All right, so we're doing problems from chapter 12 today. All right, so here are various setups. Okay, so in all these setups, the goal is to hang this sign or weight or whatever. Okay, and I'll do one of them. So just to give you a sense for how to solve these problems. And the various setups do different things. Okay, so the function is different. So let's do this one. Okay. Now, if forces are acting on a point object, then the only condition that is needed for the object to be at rest is that the sum of the forces acting on it be zero. Now, if it's an extended object, then you need this additional condition that the torque, the sum of the torques is also equal to zero on the object. Okay. Now, in this case, okay, so what we'll look at is, so the sign or weight is suspended by these three ropes, and what we'll look at is this knot, this point. Okay, so that's a point object. So for that to, so if you don't want this falling, you don't want this knot moving, and for this knot to be at rest, all we need is that the sum of the forces on the knot be zero. So there is this tension that's pulling the knot that way, the tension in this rope pulling the knot that way, and the tension here pulling it that way. All right, so let me draw a diagram. So here is the knot. This is 45 degrees. So this is 45 degrees. All right, so here's the weight, and we'll call this, so it says it's the weight of the suspended body is 100 newtons. So mass times gravity is 100 newtons. We'll just call it mg. That's 100 newtons divided by 10 gives you 10 kgs. So the mass of the object is roughly 10 kgs, which is about 23 pounds. Okay. So that's how heavy the object is. All right. So let's do this. Okay. So here's, this one is called tension 1, tension 2, tension 3. Okay, so in these problems, they just write the tension. Okay, I've given an arrow, but you see in the diagram, they just write a tension in the strings. Okay, so what you want to think of is it's like a stretched rubber band, that rope. Okay, what is this stretched rubber band doing? It's pulling this portion in that direction. It's pulling against the wall in this direction. It's pulling against this knot in that direction. You know, what does a rubber band want to do? It wants to shrink back to its original shape. Okay, so whatever is attached to the rope is being pulled in a direction such that the rope wants to get smaller. Okay. The tension here is T3. What is this tension doing? It's pulling this weight in that direction, and this weight, gravity is acting on it in this direction. So now from this diagram, you know that the tension is equal to the weight of the object. Okay? So tension T3 equal to mg. All right. All right, so now, so we'll set up our axis like this, always x-axis horizontally and y-axis like that. Okay? So what we have is the sum of the tensions. I'll explicitly write them. Oops. T1 plus T2 plus T3 equal to 0. Okay. So the three forces should add up to 0. Okay. And now both the forces are in XY are in two dimensions. They only have x and y components. So this is really two statements. The x component should add up to 0, and the y component should add up to 0. Okay? So let's look at the x components. Okay, this guy has an x component minus t1. Okay, so minus t1. And this guy has an x component. So t2 has an x component, which is t2 cosine 45. Okay, let me add another diagram, just so when you're looking at it later. So this is t2, t1, t3. Okay. So on the knot, T2 is pulling that way, T1 is pulling this way, T3 is pulling this way. Okay. Minus T1 plus T2 cosine 45 equal to 0. Okay. So T2 cosine 45 is balancing T1. So what this equation tells us is, so the x components tell us T1 is T2 cosine 45. And so what the x component of the force tells us is that T1 is 71% of T2. Okay, T2 is greater. All right, now let's look at the y components of the forces. So the y component, this guy doesn't have any y component. T2, this is y component is balancing T3, which is mg. Okay. So T2 sine 45, the y component is T2 sine 45. Okay. Minus T3 equal to 0. T2 is T3 divided by sine 45. T3 was equal to mg. So T2 is 1.41 times mg. It's 41% greater than the weight of the object. And by the way, so let's substitute this. If you put this value for T2, this divided by that is 1. So and sine 45 and cosine 45 are equal to each other, which is 1 mg. So T1 is mg. All right, so let's figure this out. Okay. Now again, you do all of this for a reason. Okay. So let's figure this out. So here's the setup. Here, let's say you're suspending a sign like that. Okay. And what we found was the tension here, T3 is equal to the weight, T1 is equal to the weight. T2 equal to 1.41 mg. All right, so my question to you is the following. So this rope, the maximum tension it's got to bear is mg. Of course, you buy a slightly stronger rope. Stronger rope costs you more money. Okay. This only has to bear mg. Here, this rope has to bear 1.41 mg, 41% stronger. Why the heck would you have the setup? You want the sign here, just take a straight rope and hang it right there. All you need is T equal to mg. Right? You guys understand the point? So you spent more money and then you had to have this kind of complex structure. All right, what this does is if you hang it straight down, it might blow in the wind. So this provides more stability. Okay? And this structure, you don't want the sign close to the wall. If you want, here's your storefront, you want the sign to, hang on the sidewalk so it can hit people on the head, right? So there's all those structures have various purposes. Yeah. And of course, the point of these calculations, what is the point of this calculation? Now you know the maximum load this rope has to bear, so you just buy a stronger rope. What kind of rope would you put there? Something that can bear twice the weight. Okay? A small 1,000 kg SUV has a wheelbase of 3 meters. If 60% of its weight rests on the front wheel, how far behind the front wheel is the wagon's center of mass, okay, or center of gravity? Okay. So this is an extended object, okay, and for an extended object, what do we have to make sure? That the sum of the forces are 0 and sum of the torques of these forces are 0. Okay, so here is the center of gravity, that's where mg is acting. And what they tell us is the front wheel supports 0.6% of the weight, 60% of the weight, and this is supporting the other 40% of the weight. Okay, so this equation is trivially satisfied. This object has mg acting this way, 0.6 mg this way, 0.4 mg this way. These two add up to cancel this force. Okay, so that equation is satisfied. Now we just have to satisfy this equation. Okay, the torque equation. Okay, what we'll do is, what is the question they ask? How far behind the front wheel is the wagon's center of mass? So we want to find this distance. Okay, so we'll call this, we'll call this the distance from the front wheel, and we'll call this the distance from the back wheel. They tell you that the wheelbase is 3 meters. That means this plus that is 3 meters. This distance is 3 meters. All right, so if we calculate, let's say we calculate the torque about the center of gravity. So this force is trying to rotate the vehicle counterclockwise. That'll give you a positive torque. This force is trying to rotate the truck clockwise. That'll give you a negative torque. Okay. So we know that xb plus xf is 3 meters, and so now we're doing this equation. Okay. And 0.6 mg times xf, there is the moment arm, there is the force, and that's a counterclockwise torque, so it's positive. and then negative 0.4 mg times xb equal to 0. Points mg cancels. See, mg cancels. So you have 0.6 xf minus 0.4 xb is 3 minus xf equal to 0. Okay, and now you can solve for xf. So 0.6 xf equal to 1.2, oops. Okay, this is 1.2 meters behind the front wheel, the center of gravity. And that makes sense. If the wheels were supporting 50% weight, then it would be 1.5 meters behind. You know? So the center of gravity is closer to the front wheel. Okay, so this is more than likely a front engine vehicle. Okay. So this says a uniform plank rests on a level surface as shown. So it's a uniform plank, okay. And so its center of mass, so you can see that its length is 6 meters. Its center of gravity is at 3 meters. This distance is 3 meters. All right, so in this configuration, it won't tip over, but if you pull it forward, if the center of gravity goes over the edge, then the plank will tip over. Okay. All right, so the plank has a mass of 30 kgs. 30 kgs is about half your weight. Is 6 meters long. How much mass can be placed on the right end before it tips? Okay. So what you want to do is you want to put a mass over there and just barely start tipping it over. Okay, so what is going on here? There is the pivot point. We'll take that as a pivot point. This weight is trying, about this pivot point, this weight is trying to rotate the plank clockwise, and this weight, the weight of the plank itself, is counterbalancing it, trying to rotate it counterclockwise. Okay, so here we're just going to do sum of the torques equal to 0. There's a third force that I didn't draw, that force, which is equal to the weight of the plank and that. Okay, that's balancing these two forces. As it's getting ready to tip. So mg times 1.8 meters, that's a clockwise torque, so that's negative, plus mg times, what is this distance? That distance is, this is 3 meters, so this is 1.2 meters. That distance is 1.2 meters. Equal to 0. Okay. The G cancels. Okay. So the mass that you have to have is the mass of the plank is 1.2 over 1.8 times mass of the plank. mass of the board itself was 30 kgs, so the mass would be 20 kgs. You put a 20 kg mass there and it'll tip over. Okay. If this gets closer to the fulcrum, what would happen to the mass that needs? You would have to increase. What if I put it right on the edge? What mass can you put there? It wouldn't matter. You could put an infinite mass. Okay. Okay, so let's do a slightly more complicated problem. So here's a boom. It's suspending a 400 Newton object. You can think of this as roughly your weight. This boom is at 20 degrees. Okay, so there's tension in the string. Okay. The uniform boom shows below weighs 700 newtons. This is your body weight. Okay, so this is roughly your weight. 700 newtons here. Okay. So what is the tension doing? The tension is holding the weight up, and there's a component of the tension that is pushing the beam against the wall. So the forces on this boom are that tension, this weight, the weight of the boom itself, and then this reaction force. So those are the four forces acting on the boom. Okay? Do you guys understand? So in our free body diagram, we want to know all the forces acting on the object, on this extended object. Here's this one force, here's this other force, this force, and that force. Those are the four forces acting on the object. And the boom is at rest. So that must mean that the sum of those forces must be 0. And the sum of the torques of these forces must be 0. Yep. All right. So we know all of that. Now let's see what is it that we want to calculate. The boom is supported by a light cable and by a hinge at the wall. Calculate the tension in the cable and the force on the hinge on the boom. So they're asking us to calculate this and this. Okay. So those are the unknowns. What we'll do is, let's first do the torques about this point. Why would you calculate the torques about that point? What would be the reason for doing that? Very good. The torque due to that will be eliminated. So that one unknown is eliminated. Okay. So, and then when we want to calculate that, so we'll get this, and when we want to calculate this, we can eliminate this unknown by calculating the torques about that point. Or if we know the torques about that point, when we know the tension, then we can calculate it about some other point. Okay, so right now, we want to calculate the tension, so what we'll do is we'll calculate, this would be a wise choice, to calculate the torque about this point. All right, so to calculate the torque about that point, so here's tension. Now what we'll do is, so we will break this tension into this component and this component. This angle is 45 degrees and this angle is 45 degrees. So this is T cosine 45 and this is T sine 45. Okay. And also we'll say the length of the boom is L. Okay. Now in the problem, they don't give you the length of the boom. So if they don't give you the length of the boom, what does that mean? It'll probably cancel out. Okay. So if they don't give you something, that means it's not needed. Okay. All right. So let's do the following. We'll calculate the torques about this point. This force is giving you a clockwise torque. This force is giving you a clockwise torque. This force is giving you a counterclockwise torque. This force is giving you a counterclockwise torque. Okay? The moment arm for this force is this length, which is L sine 20. The moment arm for this force is this length, which is L cosine 20. The moment arm for this force is that, which is L by 2 cosine 20. The moment arm for this force is that, which is L cosine 20. All right? So you have to be able to see all of that. All right. So let's do the counterclockwise torques first. So the first force is, so we are doing the sum of the torques is 0. So the first force is T sine 45. That is the force. And the moment arm for that guy is this length. And that length is L cosine 20. Plus, now here's another counterclockwise torque. This force is giving a counterclockwise torque. The moment arm for this guy is that, which is equal to this distance, which is L sine 20. Okay. So for the T cosine 45 force, the moment arm is L cosine 20. L sine 20. I'm sorry. Okay. So for this guy, that was the moment arm, and that distance is L sine 20. That's the opposite side. All right, now the negative torques. mg, the weight of the boom, times L by 2 cosine 20. For this guy, the moment arm was this distance. That distance is L by 2. L by 2 cosine 20 is that distance. And then minus 400 newtons L cosine 20. Okay. And all this should add up to 0. Okay, so it's this distance is okay, so those are the relevant distances in that diagram. Those are the moment arms, okay? All right, so now let's, what is it that we're trying to solve for? We know this, that is 700 newtons. You see, the L will cancel, and that's why it was not given. Okay? And T is the only unknown. This is 700 newtons. All right, so let's put all of that information in. Okay, so T sine 45 cosine 20 plus T cosine 45 sine 20 minus 700 into cosine 20 by 2 minus 400 cosine 20 equal to 0. So that is 783 newtons, the tension in the string, okay? So this tension is 783 newtons. That's not bad. The weight of this boom is 700 newtons, and that's 400 newtons. That's 110 newtons. So this cable is not supporting all the weight. The hinge will also be helping, okay? So the hinge will have a Y component of the force. Okay. All right, so we use this equation to calculate the tension. And now let's use this equation to calculate the X and Y components, okay? All right, so let me draw the boom again here. There's the tension, there's 400, there's 700, and there's the reaction force. So the reaction force, there's the X component of the reaction force, and there's the Y component of the reaction force. Okay, so now we're going to use this equation to find the components of the reaction force. So the X component will be Rx minus T cosine 45 equal to 0. Okay. This X component is being balanced by that X component. So Rx is T cosine 45, which is 783 newtons times cosine 45. And Ry, so let's look at the Y component of the equations. Ry plus T sine 45. T sine 45 is that component of the tension, that's the Y component, minus minus 700 newtons minus 400 newtons is equal to 0. All right, so R is 554 I plus 556 J newtons. Okay, so the X and Y components are almost equal. So this is really at 45 degrees. Okay, and you see the beam was at 20 degrees. Okay, so this is at 45 degrees and this is at 45 degrees. Okay. So it has a Y component that's supporting, holding up the weights of the beam and that. Okay, again, so let me review this problem. So to find the tension, we use this equation, the torque equation, and calculated the torque about that point. Okay, and then to calculate the reaction force, we use this equation and balance the Y components and the X components of the forces. Okay. Each step is simple. I mean, it's not that complicated, but you do have to practice. Okay, so if you look at the pages of calculation, it might seem overwhelming, but if you practice a couple of times, you'll get the hang of it. Plenty of people in the past have done it, and there's no reason that you won't be able to do it. All right, so when water freezes, its volume increases by 9%. That's an enormous increase. Okay, so ice is less dense than water, and you know this because ice floats in water. Okay. And what happens is, you might have experienced this, if you take a bottle, fill it with water, and put it in the freezer, you know, it'll pop the cork cap. Okay. In fact, in the olden days, they would use this if you had a stone quarry where the overnight temperature would drop below freezing. Then you can do the following, this trick. Okay. So let's say I'm just making up an example. Here's a stone wall, and you want to harvest this piece. You want to harvest this piece. Like this could be a marble quarry, and you want to harvest this piece. What you can do is you dig a groove here. Okay. You don't have to cut it all. Fill this with water. At night, the water freezes, it expands, and it pushes on that. And this will crack. Yeah, so the forces are enormous, okay, of the expanding water. So when water freezes, its volume increases by 9%. What force per unit area is water capable of exerting on a container when it freezes? Okay, force per unit area, that's the pressure. Okay. Atmospheric pressure is what? 15 psi. So the atmosphere exerts a force of 15 pounds per square inch. What is the pressure in your car tires? About 30 psi, so 2 atmosphere. But you'll learn that that's actually gauge pressure, meaning the actual pressure is 3 atmospheres. So the gauge pressure is the actual pressure minus atmospheric pressure. Okay? So the actual pressure is 45 psi in your cars. Okay. All right. We define a gauge pressure because most gauges, that's what they do. They measure the absolute pressure. Most gauges will measure the absolute pressure minus atmospheric pressure. Okay, so that's how they're designed. All right, so the bulk modulus is okay, so you fill this container with water, okay? And when the water freezes, what does it do? It wants to expand. The water wants to expand. It wants to expand by 9% of its original volume. So you fill this container with water. Okay, so what is it that you have to do? You have to apply forces to decrease the volume of that ice. Okay? And you have to decrease the volume by this amount, okay, by 9%. So this is 9% or 0.09, okay? So force All right, so now let's look up the bulk modulus of ice. The bulk modulus of ice at 0 degrees Celsius is 9 gigapascals. So this is 9 giga is that. Pascals is Newton per meter square. And this is 0.0905. Okay. So the volume decreases, that's negative, and it decreases by 9%. So negative, negative, positive. Okay. So this is the force per unit area. Okay. 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 This is 1 atmosphere in pascals in Newton per meter square. So this is saying the force that you need to keep the ice in the container you need is 8,000 atmospheres. Okay, 8,000 atmospheres in PSI. So this is 8,000 8,001 atmospheres, and that's roughly 1 atmosphere is 15 psi, so that's 812, 120,000, 81,000, yeah, 121,000 psi. Every square inch to keep that ice contained in, you have to apply 120,000 psi. Yeah. So you can use, if you want to apply large forces, you can use freezing water. Yeah. Okay, so a disc between vertebrae in the spine is subjected to a shearing force of 600 newtons. So when you bend over and so on, you can apply shearing forces. Look at that, that's almost your body weight. Okay. So what that is saying is, here is your disc, and these are the forces that are being applied. And this is 600 newtons. Okay. So I don't know when you apply this force. Maybe you're bent over and you're trying to lift something, but you can apply these large forces to your disc. Okay. Using a shear modulus of, again, a gigapascal, the disc is equivalent to a solid cylinder, 0.7 centimeters high, 0.7 centimeters that high. Okay. And 4 centimeters in diameter. That's almost 2 inches. Okay, 4 centimeters. Okay, so what is it that they're asking? Find the shear deformation. Okay, so what happens is when you apply this force, the disc will deform like that. Okay, and this is delta x. That is h. So, okay, so the shear deformation is the shearing stress over, okay, this is the shear deformation. How much does this top surface move relative to the bottom surface? Okay. And this is what I want you to find. So delta x over h is F over A time divided by S. All right, so the disk is the radius. So this is a top view of the disk. 2 centimeters the radius. Oops. Okay. So delta x by h equal to F is 600 newtons divided by the area pi r square. R is 2 centimeters, which is that many meters square. The disk is circular, and the shear modulus is 10 to the 9 Newton per meter square. All right. See, this is Newton per meter square, Newton per meter square. So this number is dimensionless, and that makes sense because strain is dimensionless. It's a distance divided by distance. Okay. So the strain just tells you percentage deformation. Okay. So if you use metallic objects and stuff like that, the percentage deformation is 0.1%, not even maybe 0.01% and so on. Okay. So that's what this tells you. Yep.
The board self-writing again.
Stop writing.
It's self-writing.
It's.
It's just replaying.
Oh, I see. Well, maybe, hey, it can teach us physics. This is the future. You don't have to pay anybody. So it somehow goes back to an old.
Because it was writing with you the whole time, and once you stopped to talk, it just did that.
Somehow rewinding. All right. Anyway, am I good to go?
Yeah.
Okay. So you see, this is dimensionless, and this is a percentage deformation. Okay. So what is it? Stiffer the material, smaller this number will be. Okay. So for metals and all, it's well, let's see what this number will come out to be. Okay. So again, these are two different. The delta x is a deformation in this direction, and h is in that direction. You guys understand that thicker the book, for the same force, you'll deform it more. Okay? All right. Well, I mean, for a greater height, this will be greater. Okay, so. So let's do these guys. So let's take care of powers of 10 first. This is 600, that's 10 to the minus 4. When it comes to the top, that becomes 10 to the plus 4, plus 2 is 6, and it cancels that, so you get 10 to the minus 3. So 6 divided by 4 pi into 10 to the minus 3, okay, and it's dimensionless. The 4 pi from there, okay, so. Okay, so, and if you want to get a percentage, you just multiply by 100, so that becomes 0.048%. So the deformation is 0.05%. Okay, a disc is a soft material, and that only deforms 0.06, 0.05%. So if this was a steel disc, for your weight, the deformation will be even smaller. Yeah. So to do damage to a disc, you have to be pretty, pretty violent. Calculate the force a piano tuner applies to stretch a steel piano wire by 8 millimeters. If the wire is originally 1.35 meters long and diameter of 0.85 millimeters. Okay, I'm sort of running out of time. This is a similar problem. So let me just do this problem. Yeah. A suspender rod of a suspension bridge is 25 meters long. What that means is, so here's the bridge. Oops. This is one of the cables. This is the suspender cable. Okay, that's 25 meters long. 25 meters long is the width of this room. Okay. If the rod is made of steel, what must its diameter be so that it does not stretch more than 1 centimeter? So you don't want this cable to stretch more than 1 centimeter. Okay. When 2.5 times 10 to the 25,000 kg truck passes by it. Okay, so what we're going to assume is, so here's the road, and here's the truck passing by, and this cable on the bridge is going to stretch. So I'm not drawing the whole bridge and all that kind of stuff. So here is the cable, and we are going to assume that when this truck passes by, it's only stretching this cable. This is an approximation. Other nearby cables are stretching, but assume that the rod supports all the weight of the truck. Okay, so what we'll do is we'll take this cable and suspend the truck by that. Okay. So the Young's modulus for steel is the force per unit area. The force is the weight of the truck. A is that area divided by the stretch over the length. And they tell us we want a stretch of 1 centimeters for this cable that was 25 meters long. Okay. So what is it that we want to find? What must be the diameter? So we are trying to find the area of the area of cross section. So you guys understand that thicker the cable, less it'll stretch. Okay. And so we're just trying to find the minimum thickness we want. Okay. So given the stretch, because thicker cables cost more money. Okay. And so, all right, so A is equal to F over Y delta L over L. Yeah. So I gotta look up Young's modulus for steel. Did they? Yeah, okay, so. Okay, 200 gigapascals. So the force is mg, which is 2.5 into 10 to the 4 kgs times 9.8 newtons, 200 gigapascals, Newton per meter square. Delta Y was 1 centimeters, 10 to the minus 2 meters, divided by 25 meters. All right, so that's the area of the cable, area of cross-section of the cable. So let's take care of powers of 10. There's 10 to the 4. This is 10 to the 11 and 10 to the 9. Okay, so 10 to the 4 and 10 to the 9. So what we have is 10 to the minus 5, 2.5, 2.5 into 9.8 into 25 divided by 2. And this will be in meters squared. Okay, and a centimeter is 10 to the minus 2 meters, so this is centimeters squared. So this is equal to 30.6 centimeters squared. And area is pi r squared, equal to that. So r is 30.6 divided by pi, square root of that in centimeters. So it's about 6 centimeters. So this is about how thick the cable is. Okay, so radius is 3 centimeters. The diameter is 6 centimeters, about 2.5 inches. Okay. And of course, if you have a thicker cable, it'll stretch less. You'll be able to support more weight. Okay. So that's the kind of calculation that goes on in when you. What's that?
So even if that's something that's so small like that holds so much weight.
Yeah, it's steel. Well, that's thick. And then do you know what else do they do to make it stronger?
They coil it.
In there, exactly. So make you use smaller threads and coil it just like rope. Okay. So again, what is the idea of that? You're always minimizing cost. All right, we'll stop here.